I guess we're ready to start, even though it is about a minute early. Welcome to our first press conference of Tuesday, and the third of our 8 press conferences of the week. My name's Larry Marshall. I'm the Deputy Press Officer, and I'd like to introduce Rick Feinberg, who's in the back, taking questions from the web. And Christine Pulliam is here. She will be our mic person for today. As an astronomer, of course, we're used to talking in terms of millions and billions of years. But for me, one of the more amazing things is that 19 years ago, in a room very much like this, I was sitting listening to the first press briefing about extrasolar planets around normal-type stars other than pulsars. And in that short 20 years, we've come quite a long way. Some of the recent progress in that field of extrasolar planets was discussed yesterday. This is our second press conference on extrasolar planets and their host stars. And we have 4 people today to speak on the subject who are not, interestingly enough, associated with the Center for Astrophysics directly. We didn't want you to think that they had a complete monopoly on the topic. Far from it. So our 4 speakers today are Fergal Mullally from the Kepler Science Office, who will be speaking on some new habitable zone candidates in a new release of the Kepler Planet Candidate Catalog. We're going to have Doug Caldwell from the SETI Institute talking about the validation of 12 small Kepler transiting planets in the habitable zone of their stars. Marc Kuchner and a cast of thousands is going to be speaking about diskdetective.org, the first 1 million classifications of disks. He's from NASA's Goddard Space Flight Center. And then finally, Marshall Perrin will speak of first semester science operations with the Gemini planet imager. And I believe, at least judging from the abstract, we'll actually be talking about some observations of a particularly interesting disk. So we'll start with Fergal.
Good morning, everyone. As Larry said, my name is Fergal Mullally, and on behalf of the Kepler project, I'm delighted to be announcing the release of the 6th Kepler Planet Candidate Catalog. It's a bit of a mouthful, and it includes 8 new candidate planets in habitable zones of the parent stars. These discoveries are one of the major goals of the Kepler mission, and they bring us closer than ever before to finding a sister planet to the Earth around another star. For those who would like to be reminded, the Kepler telescope is NASA's mission to find Earth-sized planets around other stars in our galaxy. It was launched in 2009, and it stared at a single patch of the sky almost continuously for just about 4 years. It was searching for transits, the shadows cast by planets as they pass in front of their parent stars. Kepler measures the brightnesses of stars, that's all. When a planet passes in front of the star, it blocks out the light from one of those stars. It blocks out part of the light, and the star seems to get a little bit fainter for a few hours. In this animation here, the small black dot represents the planet as it passes in front of the star, and the measured brightness, as shown in the graph below, drops by a small amount for just a few hours before recovering. Of course, these stars are really far away. We can't resolve the disk. We can't see it. So all we measure is that graph, that light curve. Now, the planets only transit once in each orbit. And if a planet is more widely separated from its star, it takes longer to go around. That orbit takes a longer amount of time. And so you have to watch that star for longer in order to expect to be able to find that long period planet. This explains why we look at this one patch of sky for the whole time. We want to watch the same stars for as long as possible to find the longest possible period planets. By way of an example, let me show you this model here of our own solar system with Mercury, Venus, Earth and Mars shown in it. This blue shaded region inside shows the region of parameter space in our own solar system that we would have been able to detect planets with our first catalogue, which had just the first 4 months of data in it. As we stepped through the years and we stepped through the Planet Catalogue releases, we're able to probe successfully larger portions of the parameter space of this model and of the stars that we observe, until with this, the 6th catalogue, we finally become sensitive to small planets in one-year orbits, similar to our own Earth. Of course, the orbital period of planets is not the only challenge when you're trying to find planets with this technique. Small planets like the Earth cast much smaller shadows than big planets like Jupiter and are correspondingly more difficult to detect. This figure here shows the distribution of the orbital periods and the sizes of all the candidates based on our 5th catalogue, the one we released just over a year ago, November 2013 to be exact. The horizontal axis shows the orbital period in days, and you'll note this is a log scale, so the numbers tend to get scrunched up as you move over to the right-hand side. The vertical axis shows the radius of the planet, also in logarithmic scale, but we've highlighted the sizes of the Earth, Neptune, and Jupiter for reference. These new yellow dots show the new candidates in this 6th catalogue release. There are 554 new candidates. They're mostly at longer periods, as you can see, and it includes 75 objects where their estimated radii are smaller than 1¼ times the radius of the Earth. This brings the number of candidate planets discovered with Kepler that have radii smaller than 1.25 Earth radii to over 800, and the number of candidates with radii smaller than about 2 Earth radii to over 1,200. Now, work is ongoing in this area, but we believe that the threshold between rocky planets like our own Earth and gaseous planets like Neptune or Jupiter is somewhere in the range of 1.5 to 2 Earth radii, although that number is still under active research, and we're hearing much about it in this conference. Now, for many people, they're interested not just in the small planets, but small planets in the habitable zone. The habitable zone is the region around a star where the temperature is at the right level that liquid water could survive on the surface. If a planet is too close to its parent star, it gets too hot and all the water boils off. If it's too far out, it'll be too cold, and any water on the surface will be permanently frozen as ice. This right region, this not too hot, not too cold region, depends on the type of star. Around brighter, hotter stars, that zone is further out. Around smaller, fainter stars, naturally it's closer in. The planets have to get closer into that smaller heat source. We show the habitable zone in this plot in terms of the energy received by the planet. This wraps up all these details of how far away from the star, the type of the star, the brightness, the temperature, and so on into a single number. A value of 1 in this axis means that a planet is receiving the same amount of energy from its star as the Earth receives from our own. The vertical axis shows the temperature, the surface temperature of the star. So we're splitting up these candidate planets in terms of the stars that they're around. We show Venus, Earth, and Mars in this plot for reference. The green region here shows a calculation of where the habitable zone is, where the liquid water could potentially exist around these stars, according to a recent paper by Kopper-Apru et al. 2013. And it doesn't need to be stressed enough that all these calculations of the habitable zone are estimates. They're our best guess as to where liquid water survive. It doesn't mean that we claim to detect liquid water around any of these planets. The blue circles show the planet candidates from our most recent catalogue from 2013. The size of the circle is proportional to the radius of the planet candidate. And all the candidates I'm showing here, we're restricting them to those that are smaller than 2 Earth radii. You'll notice that these new candidates that we're releasing today and that we're announcing today are systematically at around warmer stars, more sun-like stars than any of the candidates that we've released before. This is because with our extra year of data, we can probe further out around our stars, and we're getting into the region of parameter space around sun-like stars where we can detect habitable planets. Now, I should point out at this point that Kepler is publishing a list of candidates. With further observations, some of these candidates may turn out not to be planets, or as we understand the properties better, they may move around in or even outside the habitable zone. That said, these candidates represent the closest analogues to the Earth-Sun system found to date, and this is what Kepler has been looking for. We're now closer than we have ever been to finding a twin for the Earth around another star. I'd like to take the chance quickly to highlight just 2 of these candidates. They're romantically named KOI 5737.01 here. We're great at that, aren't we? As you can see from this diagram, it's around a sun-like star. It has the same orbital period as the Earth, more or less. It's the closest analogue we found to date with the measurements that we have available to the Earth. I'd also like to highlight my favorite from the catalogue. It's 2194.03. This is another super-Earth candidate. It's about 40% larger than the Earth, according to our best measurements. It's also the third planet in the system. There are two other super-Earths around this same star with periods of 35 and 68 days. Now, the analogy might be a little bit stretched, but this reminds me of our own solar system, where we've got one small planet in the habitable zone and two small planets hotter and closer in. So to summarize, I'm delighted to announce on behalf of the project 554 new Kepler candidate planets. This brings the total number of candidates to 4,175. This is an amazing number. 8 of these new candidates are in the habitable zones of their parent stars. 6 of these are around sun-like stars. These are the planets that Kepler was designed to find, and we're delighted to be finally finding them. The next steps include confirming that these detections are indeed planets, or if they're not planets, and turning these raw numbers of counts of planets into estimates of the frequency of such planets in stars of our galaxy. And with that, I'll turn you over to Doug Caldwell, who's going to tell you something about this next step of confirming planets as detections.
Thank you, Fergal. My name is Doug Caldwell, and I'm here to introduce you to 8 newly validated planets, which includes Kepler's 1,000th verified planet. So Fergal just showed us the results from the 6th planet catalog, showing the candidates here. And we can see the small planet candidates in the habitable zone, which is again represented by the green band. And while we have confidence, as Fergal mentioned, that many of these candidates are bona fide planets, we'd like to know with more certainty so that we can make accurate measurements of the planet populations in this important regime. Unfortunately for these small, cool planets, it's often very difficult, if not impossible to date, to make direct confirmation of them by measuring their masses. So to get around this, what we end up doing is trying to validate these planets by determining whether the data that we're seeing in the observations make the candidate much more likely to be a planet than to be a false positive. In order to do this work, it takes a substantial amount of work by a large community of scientists. For the planets we're announcing today, which were identified initially in the 3-year catalog from Kepler, we took observations from space using Hubble Space Telescope, from the ground using some of the world's largest telescopes like Keck and Gemini, as well as from smaller telescopes such as the Apache Point Observatory to do infrared measurements. We then used the Pleiades supercomputer to do the modeling and analysis of all this data we had collected. So collecting these additional observations along with other previously published ones and then carefully analyzing the results can allow us to say with confidence whether these candidates that Fergal's announcing are planets or whether they're rejected as false positives. So let's see, sorry. To date, this type of work has been done by the community and resulted in the verification of 5 small, less than 2 Earth radius, habitable zone planets from Kepler, all of which were identified in earlier catalogs. They're shown here along with the candidates from the 6-year catalog. So we've got a small number here. One of the key goals of doing these additional observations and analyses is that it allows us to refine our understanding of the properties of the candidate star. And that refinement lets us better determine the properties of the planet candidates that we're seeing, including their size and the energy they're receiving from their sun, from their star. As a result, these candidates can move into or out of or around in the habitable zone. So here I'm showing the updated properties of the planet candidates that were considered in the study I'm talking about today. And for example, 2 of the objects are shown here with the original position shown as a transparent disk and the new position based on better measurements shown as a lavender circle. So these planet candidates can move into and can move pretty significantly in this region as we better refine our understanding of the stars. So with this better knowledge, we can then go about saying, do we now believe that these planets are in fact true, these candidates are in fact true planets, and do they still fall in the habitable zone, and are they of this special interesting size? So as a result of this work, today we're announcing 8 newly validated planets from Kepler. These 8 planets have sizes ranging from 1.12 to 2.73 times the radius of the Earth, and orbital periods ranging from 35 to 207 days. 3 of these planets have radii less than 2 times that of the Earth, and fall securely in the habitable zone where the energy they receive from their star is not that different from that received by the Earth. With this announcement, we have significantly increased the number of these verified small habitable zone planets from Kepler. And such planets are of special interest because they have a chance of being at a temperature such that liquid water could exist on their surface. But that's not the only key thing for habitability. We also want to understand whether or not they are likely to have a solid surface, or more accurately, whether they're likely to be mostly rock like the Earth or mostly gas like Neptune. Because we can't directly measure the mass of these small planets, which are all around faint stars, we have to rely on previous measurements from other groups, such as the measurements Courtney Dressing announced yesterday, which give us estimates of planet masses as a function of radius. And we can then say that the models that they're deriving allow us to say whether our planets that we're finding are likely to be rocky or have a substantial amount of gas. So the composition range from rocky to gas is represented here as red being rock to blue being gas. And two of our objects are likely to be rocky, the Kepler 438b and 442b, and three others are in the region where they're potentially rocky, in this transition region. Now, our uncertainty about the composition in this transition region is due in large part, as Courtney mentioned yesterday, to the fact that we don't have any such planets in our solar system. So we're really relying on these observations of distant exoplanets to try and understand what these objects really are. So despite the fact that there are over 4,000 candidates from Kepler, there are still very few small, less than 2 Earth radius, habitable zone planets, and they really make up a special population that is of interest for understanding the prevalence of life in the universe. So yesterday we had 5 Kepler exoplanets in this special Hall of Fame, and today we have 8 in this elite club. And growing this sample really helps us to make a more accurate estimate of the frequency of these small habitable zone planets in the galaxy. And it's a big step towards Kepler's key goal, as Fergal mentioned, laid out at the start of the mission, which is to determine the frequency of Earth-sized planets. With the validation of these objects, the work can begin on folding these results into new estimates of the populations of these planets in our galaxy. So in summary, we've announced 8 newly validated planets, marking a significant milestone with more than 1,000 verified planets from Kepler. We have 3 of these planets are smaller than twice the size of the Earth and likely to be rocky and fall securely in their habitable zone. I'm sorry, 2 of those are likely to be rocky, and therefore they meet the two of the key conditions for habitability, temperature and size. So these validations increase our understanding of the population of planets like the Earth by continuing to fill in the neighborhood around Earth-like conditions. We're not only closing in on an Earth twin, but we're better understanding the diversity in this special neighborhood of planets. With these results, our confidence strengthens in the determination of the frequency of planets like the Earth, which is an important step towards NASA's key goal of answering the question, are we alone? Thank you. I'll turn it over to Marc.
Very exciting news from Kepler. It's hard to follow that, but it's fun to follow it because it's so exciting. I'm Marc Kuchner. I'm here today. I'm proud to represent a project called DiskDetective.org. It's a crowdsourcing project, so by its very nature, we have a large team. But I also want to mention that John Wisniewski, and we have a couple of team members in the room today. Could you raise your hands? John Wisniewski, Erica Nesvold, and I think I see Chris Lintott somewhere in the back, maybe. Anyway, you all know Chris, so he's not too hard to find. Disk Detective is all about disks, and disks are the homes of exoplanets. So the Kepler results, of course, are about planets that are discovered because they transit their stars, but most of the planets that we've found by direct imaging, so most of the planets that we have pictures of, orbit within disks. The disks, when we study disks, we are learning about how planets form. We are finding where planets are now, and we're learning about where we humans came from. So to find disks, you need a big survey. So NASA's WISE mission, with this in mind, surveyed the entire sky in 4 infrared bands. And they saw about 747 million sources, galaxies and asteroids, peaks in the interstellar matter. Among these, there are a few thousand new disks, new homes for exoplanets that we'd like to find. But the painful experience of the astronomical community is that you need to look at these objects by eye. You have to examine these images in as many bands as you possibly can to check to see whether they are really disks or whether they're one of a bunch of other possible contaminants, image artifacts, asteroids, background galaxies, background AGN, anything that shines in infrared light can end up in your sample. So to solve this problem, we asked for help. January 30th of last year, we launched a site called diskdetective.org, which is a Zooniverse site. It's a collaboration between Zooniverse and NASA. And we asked volunteers to help us find new disks by watching 10-second videos of the site, of each source. If you have a laptop or a cell phone, give it a try and tell me what you think. Diskdetective.org. So you watch a video where you see the source flash by in about 10 different bands, and you can check to see whether it's really a disk or whether it's contaminated with something else. And then you click one of these buttons to click on, and you click the blue finish button. And once you've clicked the blue finish button, that's one classification. So today we're celebrating that we received our 1 millionth classification. On Christmas Day, I learned that the project received its 1 millionth classification. And I also want to say thank you today to the roughly 28,000 volunteers who have chipped in and given me this touching present. Here's a little video where you can hear me talk some more about it. And there's usually audio to go with this. So I think I'll start that again and I'll...
Stars still surrounded by protoplanetary disks, debris disks.
Let me try that again.
Hi, I'm Marc Kuchner, an astronomer at NASA's Goddard Space Flight Center. Many of us astronomers have been searching for exoplanets and trying to learn how they form. One strategy is to search for lots of young stars still surrounded by protoplanetary disks and debris disks. These clouds of gas, rock, ice, and dust are the same types of environments that gave rise to our own solar system. From 2010 to 2011, NASA's WISE mission scanned the entire infrared sky and captured beautiful imagery. I'm most excited about this imagery because of all the new disks we can find in it. The WISE mission imaged about 500 million objects all over the sky. Only a small fraction of these sources are actually stars with disks. We can't find them with computer software because the clues are too subtle. The human eye can sort things out, but it would take years for astronomers to visually evaluate all these different sources. So last year, NASA and Zooniverse launched Disk Detective. At diskdetective.org, you can watch 10-second videos of images from the WISE All-Sky Survey and other projects. Some images show protoplanetary and debris disks, the homes of extrasolar planets. Others contain galaxies, asteroids, nebulae, and other objects. We've asked you to help us figure out which is which. Today we're celebrating that in our first year, volunteers at diskdetective.org have classified 1 million videos. The disk candidates they found went to telescopes in California, Arizona, New Mexico, and Argentina for follow-up. And we expect that the top stars from those lists will become future targets for even bigger telescopes, like Hubble and the James Webb Space Telescope, which will search for patterns in the disks and for extrasolar planets the disks may contain. We hope you'll join us as we continue our search.
So we found 478 objects of interest so far, which have become, many of them have become already targets for observatories around the world. An interesting story, one of the telescopes that we've been using for follow-up, one of our users actually introduced us to the astronomers who are doing the observations now. He lives in Cordoba, Argentina, and he got excited and he went down the street and he knocked on the door of the observatory and asked if they could observe the targets. Anyway, I just want to say if you've classified 300 or more objects and you'd like to join our advanced user group, please send an email to diskdetectives@gmail.com. And if you'd like more information, contact me, markkuchner@gmail.com. And today, happy birthday to Detective Sherlock Holmes, who coincidentally was born on January 6th, 1954. Thanks, everyone.
Good morning, all. I am Marshall Perrin from the Space Telescope Science Institute, and it's a pleasure to follow these talks about planets and disks seen in indirect methods, and to be able to talk a bit about what we're doing now with the Gemini Planet Imager to start being able to see more of them directly. I'll be giving an update on operations over the last year with GPI as it's moved from commissioning into full science operations. I'm speaking today on behalf of what I think of as a large collaboration, not 28,000 people, but maybe 100 astronomers and engineers spread across several countries that have worked together to build GPI, which is a new national facility instrument for imaging planets and disks around other stars. I'll just point out in particular the team leaders, Bruce McIntosh at Stanford and James Graham at Berkeley. And this is a project that has been sponsored primarily by the National Science Foundation and also the other Gemini partner observatory agencies in the other countries, but also in part by NASA. We saw earlier a different version of this plot showing the mass of planets, the size of planets versus their separation from the stars. And here I've highlighted the different methods that we've been using to detect these planets. You can imagine adding many more. There's now 500 new Kepler planets to add here in the transits. And it's been radial velocity and transits that have overwhelmingly been finding the majority of planets we know about today. It's only been in the last few years that we've been able to directly image and see a handful of these planets. And these are primarily the high mass planets with masses of I don't know where my cursor is on here, but in any case, the planets with masses of perhaps 8 or 10 Jupiter masses at wide separations, tens of AU, from their parent stars. And so while imaging has been limited in that we can see, basically it's the tip of the iceberg, the easiest planets to see, and easy is relative. These planets are about 1 million times fainter than their parent stars and are a small fraction of an arc second from them. But it's worth pursuing this extremely difficult observational challenge because of several benefits to imaging. One is that we don't have to wait and see a full orbital period of a planet like you do in transits and radial velocities, which is essential for these planets on orbits of 50 or 100 years. But more than that, once you can see a planet, you can start to take its spectrum. You can characterize its properties, its atmosphere, its chemistry, and start to answer some of the questions about the composition of these planets. In the long run, we think that imaging offers perhaps the best path to characterizing Earth-like planets, rocky planets on Earth-like orbits like the ones we heard about from Fergal. Probably not those specific planets, but that class of planets. That's still many, many years off in the future. Where we are right now with GPI, this is one of a new generation of instruments that have just come on sky at several telescopes around the world, dedicated to this extreme observational challenge of blocking out the starlight and seeing the planets and disks through the glare. This is the 8-meter Gemini South telescope in Chile, and GPI, you can see down at the bottom, is sort of a car-sized camera hung off the telescope there. And what's inside the box is a lot of sophisticated technology, an adaptive optics system to correct for the atmospheric jitter and deliver images with the same sharpness for the specific stars we're looking at that James Webb will see in space several years from now. An advanced coronagraph to block the starlight, an integral field spectrograph science instrument to make measurements of the planetary systems that we can see. And that's all been wrapped up in a surrounding set of operations software and data analysis software to make this not a experts-only system, but a tool we can make available to the broad astronomical community. GPI has been under development for nearly a decade now, depending on where you start the count from the project kickoff or the precursor studies. And that led us to just over a year ago in November 2013, coincidentally the same time as the previous Kepler catalog, taking GPI down there and putting it on sky and having a very successful first light run. And a year ago at the Winter AAS, Bruce McIntosh was able to share some of the first light images from GPI. At that point, those images were just a few weeks old, hot off the telescopes. A year later, those have matured into completed analyses and have yielded new understanding of the objects that we looked at. We started out by looking at some of the well-known planets that had already been seen. But the other thing that's happened over the past year is we've taken the instrument and put it through a detailed verification and commissioning program to put it through its paces, tune things up, fix a couple bugs or two, and that program was successfully completed in November 2014, just a few months ago. Happy to announce, on schedule, 1 year after first light, we took GPI and put it in the regular full Gemini science operations queue alongside the other Gemini instruments. GPI is now routinely doing a factor of 10 better than previous instruments at imaging planets and disks in the close environments of nearby stars. So even though most of the time has been spent on engineering and test calibration activities over the last year, with the small fraction of time that we spent on science verification and early science observations, GPI is already yielding a steady stream of discoveries, 8 papers in the last 6 months, which is pretty good for a new instrument. I'm going to highlight just 2 results here, imaging and spectroscopy of the well-known HR 8799 planetary system, paper led by my colleague Patrick Ingraham at Stanford, and some of my own work with collaborators, some of whom are here in the room, on looking at a circumstellar disk system around HR 4796A. And the images and text that are in your press briefing, you have a link to the Gemini website with these. So HR 8799, this is the first multi-planet image system. It's one that's been studied by many, many groups at this point over the last 4 years, or 6 years, with the 4 planets that are known around it. So what new does GPI bring to the table? This is an image we took in the very first week of operations of GPI a year ago. You can see 3 of the planets. The 4th one is actually outside the field of view in this particular image. And so, as I said, we want to move into characterizing the planets. A spectrum of planet C was obtained earlier than this using the Keck OSIRIS instrument with about 6 hours of Keck time to measure the atmosphere there. With GPI now, in actually suboptimal weather at Gemini, we were able to match that in only half an hour of telescope time. And then move beyond that to get a similar spectrum for planet D as well, so we can start comparing them. And what we found really surprised us. These 2 planets have been known to have the same brightness and the same broadband colors. But looking at their spectra, they're surprisingly different. And in particular, in the region from 1.9 to 2.2 microns, planet D has this relatively smooth spectral slope. Planet C has a sharper drop-off towards the water absorption feature at 1.9 microns. And this was not expected at all based on the prior photometry. It confirms some tentative earlier detection seen with some other instruments, and really confirms the result that these 2 planets have distinctly different spectra despite being siblings, right? They're the same mass, probably, orbiting the same star, they're the same age, yet their properties are intrinsically different. So what is that telling us? This is something that our atmosphere modelers and colleagues on the team have been wrestling with, trying to understand how to fit this. And one of the clues is this difference in the water absorption shape. If we look at Jupiter at the same wavelengths, seen here, you can see that the giant planets are complex. They have clouds, they have bands, and depending on whether you're looking at upper layer clouds or deeper into the atmosphere, you see different spectral features. And so we believe that most likely what we're seeing is a difference in perhaps more uniform cloud cover on one of these planets versus more patchy cloud cover on the other, where you can see deeper into the atmospheric layers. I'll caution that this is still somewhat under discussion. There's other possibilities with atmospheric chemistry, non-equilibrium chemistry that may explain part of this. But it's really stretching our models. And this plot here at the bottom, in black lines are theoretical atmosphere models fit to the GPI data and broadband information from a wide range of instruments. And we're really seeing that it doesn't, the models in some areas fit well, in other areas there's room to improvement. And so these data are helping really drive forward some of the atmosphere modeling. I'll very briefly highlight a result imaging a circumstellar disk. This is, again, a well-known system that's been studied before with many instruments, HR 4796. And here's a Hubble image of that disk, where you can see this is a ring around the star. This is about a 2 solar mass star, very young. You can think of this as a scaled-up version of the solar system's Kuiper belt, perhaps. So when we looked at it with GPI, here's our image. And this is a crisper, sharper image of the disk, letting us see more of the details and substructure. But more than that, using GPI, we have a polarization mode, which lets us see in polarized light. And this lets us move all the way in and see very close, the closest approach of the disk to the star. And I showed a version of this preliminarily a year ago. This is a more deeper data set we took during that year-long commissioning program I spoke of. And this data has really been pushing us to revise our understanding of the physical properties and composition of this disk. The details are rather technical in terms of modeling the scattered light properties, and I would refer you to my paper. I'm happy to take more questions later. But the short version is that reconciling the pattern we see in polarized intensity and in total intensity has forced us to think of this not as a very diffuse disk, but one that's actually dense enough to be partially opaque. And so from going from a very diffuse ring like our Kuiper belt, you can think in some ways it's analogous to one of Saturn's rings, very narrow, very slightly optically thick, to get the brightness ratio right on the two sides of the disk. And we're still thinking about the dynamics of this, perhaps hints of shepherding planets that, like in our own solar system, around Saturn's rings. So to conclude, I'll say that GPI now is moving into a really exciting phase of full operations. We've started our GPI Exoplanet Survey Legacy campaign, which will be the largest survey, deepest survey for imaged exoplanets to date, which started in November. We'll be going over the next 3 years. I'm going down to the observatory in 3 weeks for our 2.5 weeks now for our next observing run. But as I said, this is an instrument that was built not for a narrow community, but for the broader community of exoplanet imagers. And so now there's, in this coming semester, about as much science scheduled by people from the general astronomical community, not the instrument team. And so we're going to be opening up a lot of new discoveries, hopefully, over the next few years in terms of exoplanet imaging. And in the long run, taking these technologies and scaling them to future 30-meter telescopes, perhaps large telescopes in space, to continue direct imaging and push down towards the Earth-like planet regime. Thank you.
Thanks to all our speakers at this time, and we will now take questions from the audience. I should mention that Christine will have the microphone, so please raise your hand. I'll try to recognize you, and Christine will hand you the mic. Don't speak until you get the mic. Please identify yourself and your affiliation, and, of course, address your questions to a specific person. Right down here in the front.
Hi, Miriam Kramer with Space.com. This question is for Dr. Caldwell. I am curious, is there a planet that you can point to in the newly confirmed planets that is the 1,000th? Is there one that has that lucky moniker? And I have one other question after that.
Okay, I talked to the person who manages the catalog yesterday and asked her which one it was, and she said, "It's up to you. You can make it up. We don't actually keep track of them by number, so you can pick one."
Okay. Great. And then as far as the two 438B and 442B, would you mind sort of describing what it might be like to, even stand on one of those planets, like that is in the habitable zone and potentially rocky?
So 438B is the smaller of the two. It's about 12% bigger than the Earth, and it receives a little more energy than the Earth does from its star. So it could potentially be warmer. Again, we don't know if they have atmospheres or continents or even any place you could stand, but that one's the most likely to be rocky of the two. It's around a cooler star, an M dwarf, so your sky would look redder than ours does to us. 442b is about 33% bigger than the Earth, and so it's still in the likely to be rocky region, but it's a bigger Earth. And we heard from yesterday's press conference that these larger planets might take longer to have an ocean that would provide water on the surface, but it also might last longer. So these could be potentially, interesting long-term habitable planets that we're finding.
Govert Schilling, freelance from the Netherlands. I have a question for Fergal about this object KOI 573701, which you said is the most like Earth if it is a planet. Can you tell me the period of the planet, and do we have a more accurate size estimate for it? And also, I wanted to know, is there any chance of validating this particular object, and how could that be?
Okay, let me see if I get through all three parts of your planet. The period of the planet is slightly longer than 365 days. I'll have to talk to you later to give you the exact number. I don't want to say a number here and have it be wrong. Your second part, what was the second part of your question again? The size of the planet is about 30% larger than the Earth, about 1.3 Earth radii. Now, I should stress that that's based on preliminary estimates of the properties of the star. As people do the work like Doug Caldwell to understand the star better, we'll understand the radius of the planet better. It's a difficult one to validate. Would that be correct, Doug? It's more difficult to validate because it's so small, because it's so far away from a star. A lot of the follow-up, like radio velocity techniques that you would like to do, are well nigh impossible. But we can still do these verification techniques where we calculate the probability of it being a planet versus the probability of it being a false positive, and work like that. So that is possible.
Hi, Monica Young with Sky and Telescope. I had a question for Marc Kuchner. I wonder if you could say a little bit more about the follow-up that you're doing for the disks that you found, both the smaller telescopes and then eventually the JWST.
Sure, be glad to. So we follow the objects up with spectra and imaging. About half of the candidates that we get from the site and from our super users have no known spectral type. So we have to take spectra just to figure out whether it's a hot massive star, or a star like the sun, or a low mass cool star, and so on. Another reason we're doing follow-up with small telescopes is to double check that there aren't background objects. So the higher resolution, we get higher resolution images to make sure that that the signal that we're interpreting as dust isn't in fact a room temperature background galaxy that happens to be right next to the object. So we've observed already a few hundred of those 478 objects. We've reobserved them with small ground-based telescopes, and we've started applying for time on larger telescopes. One of them will probably be GPI. Marshall, hint, hint.
Talk to the Gemini guys. We don't run the tech.
To follow up our candidates. Also, while I have the mic, I just found out an email. The name of the person who did the 1 millionth classification is Tadeusz Kernowhouse, and his name happens to be, just by chance, the name in the press release, otherwise known as TED 91, the 1 millionth classification. Thank you, Ted.
More questions from the audience? In the back.
This is really exciting news from Kepler. I'm just wondering, are there likely to be...
Can you identify yourself, by the way?
This is Maggie Turnbull from Global Science Institute. Hi. It's great to see you guys. I wondered if there are likely to be future rounds of announcements regarding habitable planets around sun-like stars, or are you reaching sort of the end of the pipeline now for the Kepler main mission?
So yes, as you may have heard, Kepler ceased taking data just over about a year and a half ago when our second reaction wheel failed. While the data collection for Kepler itself is finished, the analysis most certainly isn't. We anticipate 2 more catalogues. We don't have that much more data to analyse, but we still feel we can refine and improve the way that we search for these candidates, understand the properties of the data better, and hopefully dig out a few more. On the other side of that, while the Kepler mission is dead, the spacecraft is still operating as K2, and it's going to find bucket loads of planets. Not these long period planets that Kepler was designed to find, but lots of short period planets around really bright stars, which would be excellent for follow-up with telescopes like JWST in the future.
Further questions from the attendees here? Any from the web?
Yes, we do. Okay, well, there's a whole bunch of chatter here about trying to clear up the numbers of new Earth-like planets in the habitable zone versus pre-existing Earth-like planets in the habitable zone. I'm going to go to the end of this chatter because Seth Bornstein of the Associated Press has managed to get his hands on the paper, and he wanted to have this list of objects run past Dr. Caldwell to see if it's the right list. The paper says there are 4 new habitable zone planets as opposed to the 5, or maybe it was 3 that we heard about. There's a lot of confusion here. Kepler 438b, Kepler 440b, 441b, and 442b. And that the 4 that were previously known were Kepler 62e, 62f, 69c, and 186f. And all this chatter is about how many of these habitable zone planets are really new with this announcement versus how many did we know before?
Okay, I'll try and clear this up a little bit. The paper analyzed 12 candidates. During the analysis, 3 of those candidates had been worked on by other groups and were validated as planets, and those were 186F, 296E, and F. And so that left us with 11. The 11 new ones. Of those, I'm sorry, 12 minus 3, that left us with 9. 9 new ones. I didn't do the modeling, thank you. And of those 9, one of them was not validated to the level of confidence that we've been calling for to call it a validated planet, which is 3 sigma, or 99.7% confidence. It's only like 99.2% confidence that it's a planet. So we have 8 newly validated planets. The complication is, as Fergal alluded to, what exactly do you mean by habitable zone? And for the announcement we're making here today, I've chosen to focus on the habitable zone that we've been using traditionally with these Kepler project announcements, which is this Kopperapu habitable zone. And we've been using the nominal values for these planets' radii and the flux, the energy they're getting from their star. One of the important things in the paper that Willie Torres at CFA is the lead author on is that he puts a probability on these things being in the habitable zone, not just an in or out decision. And so we've picked the 3 that are securely in this Kopperapu habitable zone. The other one you mentioned, 441b, has about a 50% probability of being in the habitable zone, and in fact all 8 of them have above a 50% probability of being in at least a slightly extended habitable zone, which is a work by another paper, Zom et al. So all of these planets have a potential of being habitable. The definition that the Kepler project has been using for habitable zone is a little bit more restricted than is in the paper. But all of these planets, the important point I think is all of these planets are small. All of them are potentially habitable. And in fact have a more than 50% chance of being in the slightly extended habitable zone, and all are interesting.
Any other questions from the web?
Yes, we have one from Tracy Watson at USA Today for Dr. Mullally. What's the radius of KOI 5737.01?
So it's about 30% larger than the Earth according to our measurements at the moment, so 1.3 Earth radii. And I'll repeat the caution that as people go and follow up on the star, understand the star better, that number is likely to jump around a little bit.
And then a follow-up question from Tracy is, why do you say these are the closest analogs to the Earth-Sun system? You don't really know yet whether the planets are actually rocky, right?
We don't know that they're rocky. With future observations, they could become larger, which will, and if they get larger than, say, 2 Earth radii, it's almost certain that they're not rocky. They are our best candidates for twins, is probably the best way to say it.
Are there any other questions from the audience? Wave your hand violently, because there you go, one over there. The lights are very bright here.
Hi, Jeff Founts, the Space Review. I think this is for Fergal or Doug. You're talking about validating these planets and turning planet candidates into planets. What's the false positive rate? How often are you rejecting planet candidates for one reason or another? And is that changing as you refine the data pipeline?
That's a very good question. And very good questions don't get very good answers. The false positive rate is really a function of what part of parameter space you're looking at. For the very large things on our sample, we have about 100 things that our measurements of the radius of the planet is greater than 20 Earth radius. There's a very good chance that many of those turn out actually to be stars that are transiting in front of another star, not another planet. As you go into as you go into short period, we also have more false positives. As you get longer period, it gets better. As we go down to these very small things, our reliability comes a little bit questionable again, because the tests that we use to weed out the planet candidates and the false positives become less effective because there's simply not enough data to do it with. So there's no one answer I can give you. Doug, would you like to sort of hazard a guess?
I think some early work by Howard and all put the false positive rate for these smaller planets was of order 10%, if I remember right. Like yeah. Most of the new 500 candidates Fergal announced are going to be planets. Whether a specific one or not we have to do a lot more work to determine that.
Other questions from the room or from the web?
Well, I hate to do this to you guys, but almost everybody there's quite a few people on the webcast, which is great, and they're still arguing back and forth over how many habitable zone Earth-like or Earth analogs there are, or habitable zone rocky planets, etc. I don't know if you can do this, but can you list all the ones we know slowly so that they can write them down and not have to ask again?
I have my slide. So the new ones that we're focusing on calling out in this announcement, which are less than 2 Earth radii, and in the habitable zone that we've somewhat arbitrarily chosen, which is this Kaparapu habitable zone. There's 438b, 440b, and 442b. So those three are added to the existing ones, which were 186F, 296E and F. Make sure I get this right. 62E and F, and 69C. No. Michelle says no. Oh, that was right. That was a warmer one. I don't have my slide to see the number. Yeah, can we put the one slide up?
Let's see, Caldwell. Yep.
Yeah, sorry. You got it. It's that one. Go back one. So 290. So the previously existing ones that meet this. Okay, yeah, the Hall of Fame. You can go forward a few slides, and there's the second to last slide actually has a.
That one?
Two more. Yeah, there you go. So that's the list of ones that meet this criteria of 2 Earth radii, or smaller than 2 Earth radii, and in the habitable zone. So they are 438b, 442b, 440b. Sorry, I was supposed to do it slowly. Are the new ones 186F, 62F, 62E, 296E, and 296F are the previously existing.
And that little blue one on the left there.
That one barely fits in the habitable zone. That's Earth.
Does anybody there online want to ask Marc about his list?
Yeah, there you go. You can borrow
Actually, there is a follow-up here.
Okay.
You're probably going to get up and walk out of the room instead of trying to answer it. So if these are the best analogs for the Earth-Sun system, what are the runners-up? Asks Tracy Watson from USA Today.
Well, I think they're in some sense, they're all the other ones that we're finding in this neighborhood. One of the things that we learned from yesterday's announcement about the composition of these planets, and from Fergal's announcement of these new candidates, is that there are a lot of of candidates and planets in this region of parameter space around the Earth, where they're about the size of the Earth, they're potentially or likely rocky, and they're getting a similar amount of energy from their star. So I think there's a long list of runners-up, and probably the real answer is we don't know. For all the ones we're announcing today, we have no idea if they even have atmospheres. We suspect they're rocky, but we're not sure. So we're really finding, I think the important thing is we're finding a lot of planets with varying characteristics in this neighborhood, and allowing for people to do further studies on a lot of different animals in this zoo.
I have a slightly more facetious answer to that. One of the candidates in our catalogue is around a star which is maybe a few hundred Kelvin cooler than the Sun. It's a little bit too big to be a rocky planet, most likely, but our measurements put it as being too cold to be in the habitable zone. So it's a runner-up because it's a candidate for an ice world. And insert your favourite science fiction reference there.
Any further questions? If not, there is one. Violent hand wave, please.
Well, if there's time, we have you here. Let's use it. So I'm really interested in the giant planets, Marshall, that you were talking about, because these guys are of approximately the same mass, and yet they have markedly different spectral signatures in their atmosphere. And I wish that the Kepler mission could find a planetary system that had like 5 planets in it that were all the same size, like 1.5 Earth radii at all different distances, so that we could finally start to figure out, what, and maybe you already do know of some systems like that, where you have very similarly sized planets all at different distances, because part of our job is to do this, what we call comparative planetology, where we're exploring how planets that you might think would be the same because of their size and mass are actually very different because of their different position maybe in the system. So I don't know who that question is for, but please comment.
I guess I will take the first comment, which is I absolutely agree in the importance of the comparative planetology, and that's why it's exciting having these new instruments that can start doing spectral characterization on a wider range of worlds. Of course, in complement with the transit characterization, transit spectroscopy for close-in worlds, I think it will remain a challenge to find multi-planet image systems. We have the one HR 8799 system, which may be a very special system, but we certainly will be looking for more analogs of that as the GPI survey goes on. I'll turn over to the Kepler guys to say if you know multi-transiting systems, certainly, but ones where they're all similar mass, I'm not sure about.
So the 2194 system that I showed, they're all similar radii. They're all the orbits that Marshall is able to observe with GPI, which is a fantastic instrument, but those are periods of hundreds of years, whereas the periods of the planet Kepler are finding are a year and under. And so there's still a lot of work, there's still a lot of instrument development to be done before we can do that sort of comparative planetology spectroscopy on the Kepler sample, which would be an amazing thing to do. But there is a lot that can be done with multi-planet systems.
I mean, the tests and the Plato samples potentially, and then we just heard earlier today about the Gaia mission's potential for finding astrometrically lots of missions. I think there's a lot of potential to make progress here in assembling, not just focusing in on the Earth-like ones in particular, but placing them in the broader context. But it'll take a while.
We have a question down here in the front.
Hi, it's Katie Mack. I was just wondering, so I know that a lot of these searches are kind of dominated by selection effects. When we're looking for small rocky worlds around sun-like stars, they're really hard to find in a lot of these different methods. And I'm just wondering, do we now have enough information to give a really reliable estimate of how many Earth-like, small rocky worlds orbit sun-like stars in their habitable zones, or are we still kind of just getting limits based on not being able to see planets like that very easily?
While I understand the importance of turning these raw numbers into frequencies, I'm not the expert on the subject. I think there's going to be another year or two of people teasing out the different subtleties of the data. I think you're going to see a lot of press results on the frequency of Earth-sized planets in habitable zones at the next AAS, and maybe for 2 or 3 AASs afterwards. I think there's still quite a bit of calculation to be done there.
Any further questions? If not, we'll thank our speakers. They've done a wonderful job. You can certainly come up and ask them questions afterwards. And before you leave, there are a few announcements. First of all, today at 2:15, we have our second press conference on the Sloan Digital Sky Survey. We hope we'll see you all there, and bring your friends. And for those of you who are signed up for the press dinner tonight, there are two alternatives. One, you can find a map to Cutter's, which is just down near the Pike Street Market. You can find those maps in a pile near the mailboxes, or you can come to the press reception, and we invite you all to come to the press reception at 5:30 in room 309. That's a press reception run by the American Institute of Physics to celebrate prize winners, and that will be going from 5:30 to 6:30, and no doubt after that people will be walking down to the press dinner, which is starts when people arrive between 6:30 and 7. Rick, do we have a firm time for the press dinner? 7 o'clock or 7 o'clock? Well, thank you very much. Thanks to all of you.